Okay, so in this video I want to show you how to determine the regression coefficients in some general mathematical form. And we have seen that in the previous example, the bivariate regression yielded an intercept of 3 and a slope coefficient of b. And what I'm trying to show you now, what I try to derive is that the slope coefficient from the regression, so we started out with a regression line where we predict a y as a function of an intercept a plus a slope coefficient b that is then related to an xi, that a can be written as, or can be derived as, the average of all y's minus the slope b times the mean of x bar. So that will be the intercept. So the first thing we see is that this is obviously a function of the slope, and the slope itself can be derived as the covariance between x and y over the variance of x. And just as a refresher again, the covariance can be written as the sum of all the deviations of xi from the mean of x times the deviation of yi from the mean of y. And then we still divide by n minus 1, but because we divide by the variance of x, and the variance of x would also be divided by n minus 1 for a sample, the n minus 1 cancels out, so we don't have to worry about dividing by anything. But the variance in words is the average squared deviation from the mean. And of course nobody really wants to know what the average squared deviation of something is, but more like what's the absolute deviation. That's why we take the square root of the variance to get to the standard deviation. But anyhow, the variance, so this is the covariance of x and y, and the variance of x is, as I said, the squared deviation from all the means. And again, we would have to divide n minus 1 and n minus 1 for the covariance, but that will cancel out here. Okay, so now let's move to the derivation. So what we do is we want to minimize the squared deviation from all the trend lines. So if we go back to our example here, the line of best fit, the trend line or the regression line, tries to minimize all those deviations of the actual observation from the mean. And because positive and negative deviations will cancel out, that will lead along the calculation to a zero, and we cannot determine anything. So that's why we need to square that. And that method is called the method of ordinary least squares. So this is what we do. So the method of ordinary least squares starts by us wanting to minimize a function f, which you see here, where we have the actual dependent variable yi minus the trend line, which is a plus bxi, and this is what we try to minimize. And again, what I'm trying to show is that a is the average of all the y's minus the slope, which we need to calculate separately, times the mean of all the x, and the slope turns out to be the covariance of x and y over the variance of x. Okay, so before I show you the slides, where I derive it here, and for the slope, let me just do it slowly in a new sheet or in a new empty slide. And let's go over the steps one by one. So we try to minimize a function which is minimizing the sum of all the deviations of y minus the trend line, and the trend line is a plus bxi. So I can put that into parentheses, or I can already subtract the slope squared. Okay, so now I have to minimize with respect to a and b, and the first order condition is that we have to find the first derivative with respect to a and set that equal to 0. Okay, so then the derivative rules with sum signs means essentially the important thing is whenever you derive, something that is a constant goes in front of the sum sign. Okay, so now we can write 2 times the sum yi minus a minus b xi. Okay, so that is the outer derivative, so we apply the chain rule, so we still have to take the inner derivative with respect to the a, and that is times minus 1. And that is equal to 0. Okay, so the minus 1 can also go in front of the sum sign, so that just turns the negative 2, the 2 into a negative 2, and then I just can divide both sides by negative 2, and then I just end up with this term. And now we can take the sum individually, and we can say, well, this is equal to the sum of yi minus, okay, so now we have to sum up a from I, so here we have I equals 1 to, let's say, in our previous example we had 6, so now we have to sum up 6 times a, well, that's nothing else but n times a, so n times a, and then we have minus b, b is considered to be a constant, and then we put the b in front of the sum sign, and we have the sum of xi. Okay, so we want to get rid of the sum signs, and there is a trick. So the sum of, for example, yi, that can also be written as n times the average of y. That's the same thing. So we can write n times the average of y minus n times a minus b, and then the sum of xi we write again n times x bar equals 0. Okay, so now we are almost done. We want to solve for a. First thing I can do is I can just divide both sides by n. Again, then it disappears here, disappears here, disappears here. And then we just rearrange the terms. And then we can put a on one side of the equation, and then we get the result that a is indeed equal to y bar minus b times x bar. So that is the first result. Okay, so next we do the derivative with respect to b. And so now what we do is we can already, because we have a b in A2, so we can already plug that into our original function. So what we want to derive is actually, so we start now with min f equals the sum of, okay, there's a yi minus, so for a I write now y bar minus b x bar minus b xi squared. Okay, so we just replaced a with the b. So let's take a look at this one. We have a b here and a b there, so maybe it makes sense to already consolidate that a little bit. So we can write min f equals the sum of yi minus y bar. Okay, so then we have plus minus times minus b x bar minus bxi. Okay, squared. So now let's write it like, so yi minus y bar, that already looks a little bit like the covariance. And here minus bxi minus x bar, so if I flip that around, I can actually rewrite that as the sum of yi minus y bar, and then I put the minus b in front, minus b. Okay, so now I factor out the xi, minus b times xi, and then I have still here the x bar, but I need to make that also a minus, because minus times minus is plus. So minus x bar. Okay, maybe another parenthesis squared. So you see that has already the element a little bit of a covariance. So now let's take the derivative. So now df with respect to db is, okay, it goes in front, so we have 2 times the sum of yi minus y bar minus b times xi minus x bar. Okay, so the 2, we have to subtract 1 from the 2, but now we still have the inner derivative. So we still have here the derivative with respect to b, that leaves us with a negative 1. So let's write here negative 1 times xi minus x bar. So okay, that was then the chain rule, and that is equal to 0. Okay, so the negative 1 can go in front of the 2, so then here we have a negative 2, and we can get rid of this one here. Okay, so now we are almost done. So now let's just consider those two terms. Let's put here another parenthesis around. And now what we do is we multiply. And by the way, before I forget, we divide both sides by the negative 2, so then it's gone. Okay, so now what we can do is we can just write, okay, so this is the sum of yi minus y bar times the xi minus x bar, which is outside the parentheses. So this is yi minus y bar times this term. And you see this is already part of the covariance. Okay. And now I still have here minus b. Okay, minus b times xi minus x bar, but there is another one, so I just can square it. Okay, and this is again all in one parentheses. And now I can write the sum individually. So now I get the sum of yi minus y bar times xi minus x bar minus b, that can go in front of the sum sign, xi minus x bar squared equals 0. And you see to the left we have the covariance, and here we have the variance. So if we solve for b, I have to now be careful with the space on the slide, we get the sum of xi minus x bar times yi minus y bar over the sum of xi. Okay, so it's already run out of space here. Let me go over there quickly. Xi minus x bar squared. Well, that is nothing else but b is nothing else but the covariance of x and y over the variance of x. And this is what we tried to show. Okay. All right. So I have also derived it on the next slides. So let me go again here. You can follow those steps. I will not go over them again. And here the same for the slope. And what's more important is, let's actually try and replicate the result. So in the previous example, we had again, so this was our data here, and we had an intercept of 3 and a slope of 1, and this was our data in that little table. So let's double check. So here's the same data, xi and yi, and actually I should maybe not have capitalized that one. But anyhow, so we want to test that the intercept is indeed 3. So we need the mean of y and the mean of x. So the mean of y is 6 and the mean of x is 3. So we can write, maybe let's put that here, y bar equals 6, x bar equals 3. Okay, we don't know b. We need b in order to calculate a, but we know b is the covariance of x and I, and the covariance is the sum of all the deviations of x from the mean. I mean the product of all the deviations of x from the mean of x times all the deviations of y away from y. Okay, so you see xi minus x bar is 0 minus 3, negative 3, 2 minus 3, negative 1, 2 minus 3, negative 1, 4 minus 3, positive 1, 4 minus 3, positive 1, 6 minus 3, positive 3. And of course, all those deviations from the mean, they sum up to 0. That is what makes the mean the mathematically most accurate measure of central tendency, because all the deviations from the mean are 0. And so now we do the same for y. We take every individual y and subtract from it the mean of 6. So 3 minus 6, negative 3, 6 minus 6, 0, 4 minus 6, negative 2, 9 minus 6, 3, 5 minus 6, negative 1, 9 minus 6, 3. So now what we do is we just multiply that. So we have negative 3 times negative 3, 9, negative 1 times 0, 0, negative 1 times negative 2, 2, 1 times 3, 3, 1 times negative 1, negative 1, 3 times 3, 9, and we sum that up. So that means we have, for the covariance in the numerator, the 22. So now we have to divide by the variance of x, and again we don't have to divide by n minus 1, because that would cancel out. So, but the variance is the squared deviations from the mean. So we have already calculated xi minus x bar. So we just need to calculate that. So negative 3 squared 9, negative 1 squared 1, negative 1 squared 1, 1 squared 1, 1 squared 1, 3 squared 9, that's also 22. So in the numerator we have 22, and of course that is pure coincidence. There's no hidden law that the covariance is always equal to the variance, but you can see that formula, applying that formula, indeed gives us a slope coefficient of 1. And now we can calculate the intercept, which is the mean of y, which is 6, minus b 1 times the mean of x, which is 3. That is 3. And that is how we calculate the slope and the intercept in a at least very simple bivariate regression. Once you have more variables, of course, things become a little bit more complicated, but the spirit is still more or less the same. But anyhow, in order to get a basic idea of the underlying math, I think that's good enough for now. And you should have an idea. What's important is that you remember that the formula for the slope coefficient, covariance of x and y, or the variance of x, and the formula for the intercept, which is y bar minus b times x bar. Okay, let's stop here, and then let's continue with the concept of unbiasedness in the next video.